Welcome back, everyone. We have reached the 12th and final episode of the Artificial Vision Systems course. In today's episode, we're focusing once again on the last part of our vision system, the software. In the previous episode, we touched on some basics of image processing and saw how it's possible to obtain a pixel measurement of the object captured in the image. Today we'll continue talking about software, but this time we'll see how it's possible to go from information in pixels to information in a known unit of measurement, like millimeters, for example. In this case, we'll be talking about camera calibration. Why do we need to calibrate a camera? Because an image by itself doesn't provide any information about the actual size of the objects being captured. Let's take this picture of a tree as an example. With nothing to compare it to, we have to rely on our experience to say that this tree is probably big, maybe a few dozen meters tall. But when a reference object appears, like this pot, our brain changes its perception and tells us that this tree isn't big at all. Is it a few dozen meters? No, it's actually just a few dozen centimeters, since it's a bonsai. Before seeing the pot, you might have thought it was a tree you'd find in a forest. But that's not the case. So, what does it mean to calibrate a camera? Calibration allows us to convert a measurement taken in pixels, the unit of measurement for the camera, into a real-world unit, like millimeters. With image processing, you can get the measurement in pixels, and with calibration, you can get that same measurement in millimeters. After seeing what calibration is for and what it means to calibrate a camera, let's now look at how image calibration is done by comparing with known objects. The goal is to find the pixel to millimeter ratio that allows us to easily switch from one unit of measurement to another. Just like in the books about dinosaurs we read as kids and adults, you need a known element, in that case, the person drawn next to the dinosaur, to understand how big it is. The same thing happens in vision systems. In this case, though, the comparison is made with known objects, meaning objects with known dimensions and known characteristics. These objects are called calibration templates and are represented, for example, by grids of dots or checkerboards. Since calibration templates are completely known, they allow us to determine the millimeter to pixel ratio, thus let us calibrate the camera. Now let's see how you can actually calibrate a camera. In other words, let's understand how it's possible to determine the pixel to millimeter ratio. To do this, we need to define a mathematical model and talk about the relationships between different reference systems. Let's define three different reference systems. An image reference system, located where the sensor is positioned. A camera reference system, located at the point of the optical system where the light rays enter. A world reference system, located outside the camera. Now let's add a point P somewhere in space. Point P can be expressed using any of these reference systems. In world coordinates, in this case P compared to W has coordinates xw, yw, zw. In camera coordinates, in this case P compared to C has coordinates xc, yc, zc. Or in image coordinates, and in this case, P compared to I has coordinates xi, yi. Finally, let's compare the camera reference system C to the world reference system W. The origin of the reference system C has coordinates to the world system W equal to cxw, psi w, czw. When we take a measurement on an image, we're actually getting the coordinates of the captured object in comparison to the image reference system I. The goal is to find those same coordinates in the world reference system W. The image reference system I works in pixels, while the world reference system W works in millimeters. To be able to go from I to W, the most common model involves passing through the camera reference system before reaching the world reference system. These two transformations from image to camera to world are called perspective projection and coordinate transformation, respectively. This step is necessary because in the image we work in 2 dimensions, since the image is flat, while in the real world we work in 3 dimensions. This transition from the image reference system to the camera reference system is what allows us to obtain the third dimension. Then we add another variable. In the image, we think in pixels. In the camera, and therefore in the real world, we think in millimeters. Let's start by focusing on the first conversion from the image system to the camera system. A point P and I with coordinates xi and yi. On the image plane, it can be obtained from the relationship that links the camera system C to the image plane I. We know from geometric optical system that the image plane is at a focal distance from the camera. The focal length is the distance used to go from the 2D domain to the 3D domain. Let's also consider that when working on an image, the reference system is placed at the top left of the image. On the sensor plane, however, the origin of the reference system is conventionally positioned at the center. Finally, as we've mentioned, we also have to keep in mind that in the image, so at the sensor plane level, there are pixels. Whereas in the camera, measurements are in millimeters. So we'll need a conversion constant from pixels to millimeters. All these relationships are mathematically described by these equations. I and j are the coordinates of the point compared to the image plane. xc, yc, and zc are the coordinates of the same point compared to the camera reference system. To move from one domain to another, I use factors such as fx, fy, ox, and oi, which allow for 2D to 3D conversion, pixel to millimeter conversion, and shifting of the reference systems. fx, fy, ox, and oy are called the intrinsic parameters of the camera and can be obtained through the calibration procedure. To be able to determine them, I, j, xc, and yc, and zc must be known. All of this concerns perspective or intrinsic calibration. Now let's look at the part about coordinate transformation, also known as extrinsic calibration, which is the process that allows us to go from the camera reference system to the world reference system. In this case, we have two 3D reference systems, a camera system and a world system. A point P can be expressed in either of these two systems. To be able to move from one reference system to another, we need to find out what the relationship is between the world and the camera. When we talk about extrinsic calibration, we're basically talking about moving from one 3D reference system to another 3D reference system, which is located somewhere else compared to the original reference system. To go from one system to another, you generally need to apply a rotation and a translation. The rotation is used to rotate all the axes of the starting reference system in comparison to the origin of the reference system itself. The translation is used to move the just rotated reference system through space. The rotation is usually described by a 3x3 matrix, called the rotation matrix, which contains 9 interrelated values. These 9 values can be obtained from 3 independent values that represent the 3 rotation angles along the 3 axes of the reference system. The translation is usually described by a vector of 3 values, which correspond to the components of the vector that connects the origin of the starting reference system and the origin of the destination system. By combining the rotation matrix and the translation vector, it is possible to determine the coordinates of point P in each of these two systems. This is the relation between them. The R parameters and the T parameters are obtained through the extrinsic calibration procedure. Again, to obtain these parameters, you need to know the coordinates of the point both in the camera reference system C and in the world reference system W. Calibrating a vision system means going from an image to a camera system and then to a world system. To do this, I use both the intrinsic and extrinsic parameters. Calibration is specifically used to derive these parameters, starting from the coordinates of certain points in each of these systems. At this point, how do we obtain these values? We use the calibration templates we saw at the beginning of this episode. The most common calibration procedure actually involves using, for example, a chessboard. Using some image processing algorithms, I can extract certain known points from this chessboard, such as, for example, the corners of said squares. For these corners, I know both the coordinates compared to the image plane, because I just extracted them, and the coordinates compared to the world system, because the calibration template is already known. Through the relationships we saw earlier, we can therefore use these coordinates to obtain both the intrinsic and extrinsic parameters. Once I know the intrinsic and extrinsic parameters of the camera, I can work in reverse. Given the coordinates of the point in the image plane and the intrinsic and extrinsic parameters, I can determine the same coordinates in the world reference system, thus obtaining the actual measurement. By knowing these parameters, we are able to easily convert a measurement in pixels, obtained by analyzing the digital image, into a measurement in millimeters. This way, we have achieved the goal of the course, effectively being able to measure an object using our vision system.